Okay, physics time. So, we're talking about gravity. Let's just do a little bit of a recap of what we're supposed to know about gravity. Starting with the fact that in a gravitational field, the force due to gravity on an object is equal to the mass of that object times g, and g is the gravitational field strength. It's how much force due to gravity is applied on an object per kilogram. So g is newtons per kilogram. Now we also know that when there are two objects with mass, they will attract each other due to the gravitational force. Now it's very small on small masses, so two people walking along aren't going to be drawn together because of gravity. The force between two people is going to be extremely small, so that's no excuse to get close to somebody who you might particularly like. Force equals constant, big G, times mass of one object times mass of the other object divided by the distance squared. So it's an inverse square law, we call it. Now, we can compare these two equations and see that the force on an object in a gravitational field is mg, which is also equal to big G times the big mass times the small mass divided by r squared. Put the two together, mg equals big G, big M, that might be the mass of a planet say, little m, that might be the mass of a satellite orbiting a planet, divided by r squared. Now what we see here is that the mass of the orbiting object, or the object mass of the smaller object, appears on each side, so we can just cancel it out. So we get an expression for g, the gravitational field strength. In the gravitational field strength is equal to big G times m divided by r squared. Big M is the mass of the larger object. So if we're talking about, say, a plane in the sky, we want to find out that how much the gravitational field strength, well, it doesn't need to be a plane in the sky, it can be anything. The gravitational field strength is due to the mass of the larger object, not the mass of the object itself, the mass of the larger object. It is big G times big M divided by r squared. That's gravitational field strength. Okay, let's talk for a moment about orbital speed. How fast does an object need to travel in order to stay in orbit around a planet? If it goes too slow, it will spiral towards the planet, crash and burn, and that's the end of that. If it goes too fast, it will leave the planet and disappear forever and be lost in space, and it will be a total disaster. It has to travel at the right speed. How do we know the speed? Well, we know that the centripetal force has got to be equal to the force due to gravity. If those two forces are equal, then the object will just orbit nicely, the way you want it to. So we know the centripetal force is mv squared divided by r. That's the mass of the object that is orbiting. Now it equals the gravity force, which is big M, mass of the planet, little m, mass of the orbiting object, big G divided by r squared. So if we look at this, what we find is the orbital speed can be found by cancelling out the two m's, cancelling out one of the r's, so we see v squared equals g m over r. Therefore the orbital velocity is simply square root of big G, gravity constant, mass of the planet divided by r. That is useful. Let's talk about the orbital period for a moment. Excuse my interesting form of duster. Now, orbital period. Period of orbit. Period is the time taken to orbit. So consider we've just covered the fact that V squared equals big G, big M divided by R. Now, we also know speed equals distance divided by time. What's the distance around an orbit of a planet? Well, it's 2 pi times the radius, not the radius of the planet, the distance the orbiting object is from the centre of that planet, divided by 2 pi r divided by t. So t is the period. So if we have this here, we can substitute for v 2 pi r over t. Therefore, 2 pi r over t squared equals big G M over R. Now, you can start to see there's going to be a lot of r's in this equation. What we end up with is, so if you square that, we get 4 pi squared r squared over period squared equals big G M over R. So that simplifies down to, therefore, t squared equals 4 pi squared r squared r cubed over big G M. To get from there to there, I've missed a couple of steps so I don't run out of whiteboard in time. Square root the whole thing, period equals, there's different ways you can write that, so let's just go 4 pi squared r cubed over gm. And there you have an expression or an equation for the period of an orbit. Finally, the velocity that an object will have to travel at to actually escape the gravity of a planet. We call it escape velocity, strangely enough. So you're trying to get away from an alien planet that you've been stranded on, and you find a spaceship and you take off and you want to know how fast do I have to go before I run out of fuel that I will actually be able to escape this planet and get back to Earth. I mean, this might change your life. This is important stuff. So the work, we all know that the work done, or energy required, equals force times distance, which we will call r. That'll be the distance out from a planet. Now the work done to get away from that planet will be supplied by the kinetic energy that you get somehow from the engine, which is half mv squared. So we've got a sort of a starting place here. So the force will be supplied by, force is holding you there is gravity, and that force has to be overcome somehow. It will be overcome by the kinetic energy supplied by the engine. So force due to gravity is big G, big M, little m over r squared times r. So you can already see one of those will cancel out, equals half mv squared. Now again, m's will cancel out, so we end up seeing that what we get is half v squared equals big G big M over r. That's the mass of the planet. Simplify that, we get v, escape velocity, equals square root of 2 g m over r. Big M, the mass of the planet. Okay, there we go. That's escape velocity.